Le Chatelier Principle. So we have learned about equilibrium. Looks something like this. And you're going to have a forward reaction and a reverse reaction. Notice here how we have a gas, we have a gas, we have a gas, and then we have a solid. So we already learned that the rates are the same, the amounts are different. We learned how to find the moles or the concentration at equilibrium. Now we're gonna learn one more thing, and that is what would happen if we have an equilibrium reaction and we end up disturbing it. We end up adding A or remove B, or we change the temperature, we change the pressure. Like, what is going to happen to the amounts and the concentrations of each chemical? So it says here, if you do something to disturb a system at equilibrium, the system will respond. And it's going to respond in a way that it will partially counteract that change. So the key word here is counteract. So there are two possible disturbances. You could change the concentration, or you could change the temperature, and that will trigger these amounts and concentrations to change. And so we're going to start with the first example here. It says we have a reaction. We have A and B reacting, and it's going to produce C and D. And here we have a solid, and it's going to be reversible, so it's an equilibrium reaction. And the question is saying what would happen if you add more A. So what would happen if you disturb this reaction by adding more of this? So you throw A into the system. How is the system going to respond? So again, the system will respond by countering that change. So if we're adding more A, then that means that we need to lessen that amount, okay? That means that whatever is on the left side needs to be reduced to counteract the addition of substance A. So if we add more A, then the system is going to want to get rid of some of it. And the only way to get rid of some of it is to go to the right. So it says that means you have too much A, and to counteract this change, we need less of it. And the only way to do this is to shift the system to the right so more A can be used up. If the reaction shifts to the right, okay, so we're going to put right. If it shifts to the right, that means we have the following changes in amount. So we initially added more A, right? So we're going to put an upwards arrow right here. Okay, so we're going to have, let me see if I could find an upwards arrow. We're going to have more A, because even though it's shifting to the right, we're going to start off with more A because that's what we're putting in. And because it's shifting to the right, that means we're going to have less B. So we're going to have less B. And again, it's shifting to the right, so we're going to end up with more C and more D. Okay, so the amounts definitely change. Okay, so that's what's going to happen after equilibrium is reestablished. I know it sounds a little confusing here because you're like, oh, it shifts to the right, then why don't we have less of A? And the reason we have more is because we initially added a little bit. We initially added A. So therefore, we're going to have a little bit more after equilibrium is established, while B is going to be less than what we started with. And we're talking about the amount. But when we consider volume, right, moles per liter or concentration, we're going to see something similar. A is a gas, right? B is a gas, C is a gas, solid. Solids, we learned that solids don't change in concentration. So right here where it says D, we're not gonna see a change. Okay, so there's not gonna be a change, no change. So I'm gonna put a little bar there just to show that there's no change in D, because in an equilibrium reaction, the amounts do change, but the concentrations don't. And here, because we increase the amount of A, that means we're gonna have more A in terms of concentration, and we're going to have less B. We're going to have more C. And again, the concentration of D, the solid, does not change, even though the amount did. So there's a difference between the two, and I'm sure you'll get the hang of it. So let's try example 2. Hopefully we will get it by then. It says, let's say we have the same reaction. What would happen to each substance if you remove substance B from the system? Is it going to shift to the right? Is it going to shift to the left? Are you going to have a higher A, a lower A, a higher B, a lower C, a higher D? Like, what's going to happen to the concentrations and the amounts of each? So basically I rewrote the same format here. It says if the reaction shifts to the blank. So let's look at this. It says, what would happen to each substance if you remove substance B? So you have less of this. So you have to think, I have less B. Therefore, to counteract that change, I need more of it. I'm going to need more B. So if I want more B, then that means it's going to shift to the left. Okay, to the left, because you're going to produce more B to make up for that loss. So I'm going to put here, if the reaction shifts to the left, that means we have the following changes. So again, we initially removed B. Okay, so we should start with that. We're going to reduce B because that's what we did. So at the end, after equilibrium is reestablished, you'll see less of it. Even though the reaction is shifting to the left and you're producing B, but you're still going to have less of it at the end in comparison to what you had at the beginning at equilibrium. So because we're shifting to the left, we're going to have more A. So there's going to be more A. Okay, ideally, you're going to make a little bit more B, but overall, there's going to be a drop because we removed B. Okay, here in the question it says you remove B. So even though we're producing a little bit more, overall we're going to have less of it after equilibrium is reestablished. And because it's shifting to the left, you're going to have less C and less D, right? So less and less. Okay. Therefore, we have the following changes in concentration. So we'll have more A because, the amount of A changes. And it's a gas, so it's not constant. B goes up, goes down. It's a gas. C goes down because its amount goes down. But D is a solid. It is constant at equilibrium. So its concentration, even though we have less D, the concentration is actually going to be the same. Okay, the concentrations don't change when you have a solid or a liquid at equilibrium. The amounts do change, but not the concentration. Okay, there's a rule here that you need to remember. Anytime we change the amounts by, for example, 3, it says, let's say we have this reaction. We have A, it's a gas. We have B, it's another gas. And it's producing 2 moles of C, and it's a gas. And you're producing D, which is a solid, and you're producing energy. So it says, what would happen to each substance if you increase the temperature? What would happen if you increase the temperature? So you're going to treat energy as a chemical. Pretend it's a chemical. If you crank up the temperature, that means we're going to have more energy. And if we have more energy on the right side, then that means that it's going to want to counter that change. The system is going to counter that change by shifting it to the left. Okay, so treat the temperature as if it were a chemical. The system will shift to the left to counter the disturbance. If the reaction shifts to the left, that means we have the following changes in amount. So that means we're going to have more A, more B, and then less C and less D. If the reaction shifts to the left, that means we have more A, we have more B, right? And then we have less C and less D. The amount of D, even though it's a solid, it does change, but remember its concentration does not change. Okay. So if A goes up, then the concentration of A goes up. If B goes up in amount, then its concentration goes up. And then if C goes down in amount, then its concentration also goes down in amount. And D, because it's a solid, it's constant under any condition. Okay, so maybe you guys can try this one. What would happen if the temperature dropped? Go ahead and try this one. You're going to use the same equation right here. Okay, so now that you tried, less temperature means this guy is going to drop. And if this drops, the system is going to counteract that change by making more of it, right? So it's going to shift to the right. So right here, you're going to put right. And that means we have the following changes in amount once equilibrium is reestablished. So if it shifts to the right, that means we're going to have more C and more D. So more C and more D. And then you're going to have less of this, right? Because a shift to the right means you're consuming this. So you're going to have less A and less B there. So the solid concentration will not change. So I'm going to put a bar there. And we have a drop in A. So that's going to trigger a loss in concentration and a loss in concentration of B, and then higher concentration of C since its amount went up. Sure. So it says here, key idea, the value of K doesn't change. It doesn't change with concentration, but it does change with temperature. So just keep that in mind. In gases, we learned that they generate pressure. The more collisions with the wall of a container, the higher the pressure, right? We were to increase the volume like a balloon, it expands. Therefore, there's going to be less collisions with the container, and so the pressure goes down. Okay, and vice versa. So just keep that in mind for now. This idea of expanding and a lower pressure. Since the volume has changed, the real disturbance is a change in concentration. So we learned that concentration is moles per liter. So if we increase the denominator here, right, we increase this, then that means the concentration goes down. So this means that increase in the volume means a drop in concentration and vice versa. However, it's probably easier to just think of pressure as a disturbance. So if you guys memorize this trick, then you'll know how to solve these type of problems. So it says, the system will shift to the side with less gas particles to decrease the pressure. So if you want the pressure to go down, let's say the volume, let's say the volume went up, right? And the pressure went down. And because the pressure goes down, the concentration goes down. So to counteract that change, you want more pressure. Then that means you're going to want to move the direction of equilibrium to the side where there's more gas particles to increase the pressure. Or we have 2 moles of NO2, and it's at equilibrium and it's forming N2O4. And it says here, what would happen if the volume of the container was increased? So you have this in, let's say, a balloon. And what it says, what would happen if the volume of the container was increased? This would cause the pressure of all substances to go down, right? To decrease. So I'm going to put my downward arrow. It's going to decrease. And if the pressure goes down, the only way to counteract that is to move in a direction where you're going to trigger a higher pressure. So if the pressure goes down, you need to increase the pressure. That is how you counteract. And the way you counteract that is by moving in the direction where there's more gas particles. So here's one gas particle of dinitrogen tetraoxide. And here there's 2 moles. So because the pressure dropped, you want to move in the direction where there's more moles, which is this side, 2 moles versus 1. So that means the reaction is going to shift to the left. So I'm going to write left right here. If the reaction shifts to the left, then that means we have the following changes in the amount, meaning that we're going to have more NO2 and less N2O4. Okay, so, and all of these are gases, so their concentrations will be directly affected. So if that goes up, then that goes up, its concentration goes up. And if this concentration, this amount goes down, then this concentration goes down. Okay, so hopefully that made sense. You just have to think about it like, okay, if you disturb a system, it's going to counteract that change. It's going to move in a different direction. And if it moves in a different direction, the amounts are going to change. And then if the amounts change, then the concentrations may change if the substance happens to be a gas or a aqueous substance. So here is a table. And what I want you guys to do is try to fill this in, and once you're done, just check in with me and we're going to go over it one by one. It's like 1, 2, 3, 4, it's like 5 problems all in one table. So you're going to tell me the direction. Is it going to shift to the right or left? What's going to happen to the amounts of each substance? What's going to happen to the concentration? And then what's going to happen to the K value according to the rules, or the general rules that we talked about. So hopefully you guys try that. All right, now that you guys tried, we're adding carbon. So we have more carbon. So that means that it's going to want to counter, the system's going to want to counter this change by decreasing the amount of carbon slightly, right? Slightly decrease. And the way to do that is by shifting to the right. So I'm going to shift to the right. So I'm going to put a right arrow. And if it shifts to the right, then that means that, you know, we're going to have less of this. But remember, carbon is something we initially added. So we're actually going to have a little bit more than what we started with, because that's what we added. Okay, added. And because it's shifting to the right, that means we're going to have less of this. And we're going to have more methane. And carbon's concentration, it's not going to change at all because it's a solid. And because H2 goes down, its concentration is going to go down, and methane's amount went up and it's a gas, then its concentration will also go up. And the K is unaffected by a change in concentration. So it's not affected at all, the K value. For methane, we're adding this right here. And to counteract that change, it's going to want to shift to the left, right? We have more of this. It's therefore it's going to shift to the left, so we have a little bit less of it. So left, that means we're going to have more carbon, more H2, and again, we initially added methane, okay, and it's shifting to the left, but that means that you're going to get rid of some of the methane, but because we added methane in the first place, you're actually going to have a little bit more, okay, because it's a partially counteracted. So the keyword here is partial. And the concentrations can change depending on the state of matter. So if you recall, solids don't change. So carbon is not, concentration is not going to change. And because these two chemicals went up in amount, then their concentrations will also go up. And the K value is unaffected by amount added or removed. The next one is hydrogen is removed, so we're removing this, and the only way to counteract that is to make more of it. So there's going to be a shift to the left. So a shift to the left, and that means we're going to have more carbon because it's shifting to the left, but also you're going to make a little bit more hydrogen. But because we've removed some of it as a disturbance, you're actually going to have less of it after equilibrium is reestablished. And because we're shifting to the left, that means we're going to have less methane. Okay, the concentration of carbon is unchanged because it's a solid. Right here, it's a solid, so the concentration does not change. And because these two chemicals drop in amount, they're gases, they're going to drop in concentration. And the equilibrium constant is not going to be changed because the equilibrium constant only changes when there's a change in temperature. And then temperature is decreased, so this goes down. So in order to counteract it, it's going to change by adding more energy, and that means it's going to shift to the right if we want to make more energy to make up for this drop in energy here. So it's going to shift to the right. Okay, and if we shift to the right, that means we're going to have less carbon, we're going to have less hydrogen, we're going to have more methane. And the concentrations are unaffected for solids. A bar there. And because this guy goes down and this guy goes up, then that's going to be the same for concentration. And the temperature does change the equilibrium constant, so we're going to put yes. Okay, if you need to know how does it change it, because we're moving to the right, that means the K value is going to be bigger. Okay, so whatever the K value is, it's going to be a little bit bigger because of this drop in temperature. Okay, so the last example is volume. So it's related to what we talked about in terms of pressure. So the volume decreases, so that means the pressure is going to go up. And if the pressure goes up, then that means we want to move in the direction where there's less moles, there's less particles, to reduce the pressure, partially reduce the pressure. So just think about it. You decrease the volume, that means there's higher pressure, particles are colliding more. The higher the pressure, the more concentrated the gas becomes. And the only way to reduce the pressure is to move in the direction where there's less moles. So again, the pressure went up, but we want to reduce the pressure because that's what equilibrium reactions do. They counteract the change. And the way the system will counteract it is by reducing the pressure, by moving in a direction where there's less moles. So here I see 3 moles on the left side, 1 and 2, 3 moles on the left and 1 mole on the right. So which side has more moles? The right side. So it's going to shift to the right. And if it shifts to the right, that means we're going to have less of these guys right here. And we're going to have more product. The concentration of carbon is unchanged because it's a solid. And because these concentrations change, they're going to be directly proportional to their concentration. So that means this is going to go down and this is going to go up. Okay, so the amount goes down, the concentration goes down, the amount goes up, the concentration goes up. And the equilibrium constant is not changed because the temperature is not being changed. And this closes the unit for equilibrium.